In the faint glow of a distant star-forming region, the James Webb Space Telescope has captured a scene that defies previous assumptions. Each little red dot isn't just a star, but a swirling cocoon of gas and dust where new stars are being born, rewriting our understanding of stellar nurseries in the early universe. These faint, glowing spheres, once thought to be mere background noise, are now revealed as dense clouds of molecular hydrogen, glowing faintly in the infrared. Their reddish hue isn't just a trick of light, but a signature of heat trapped within these cosmic cradles, where gravity is compressing gas to ignite nuclear fusion. This isn't just a pretty picture, it's a window into the earliest days of star formation, possibly even older than our own Milky Way. The image, sharper than any before, forces astronomers to reconsider how galaxies like ours might have begun, with these hidden furnaces lighting the dark expanse of the cosmos. What we thought were isolated points of light are now storytellers of the universe's infancy. In the vast expanse of space, there are certain images that capture the imagination of scientists and the public alike. One such image, recently unveiled by the James Webb Space Telescope, has sparked a wave of curiosity and scientific inquiry. At the heart of this discovery lies a long-standing mystery, the so-called little red dots that have appeared in space photographs for decades. These tiny, glowing specks, once shrouded in uncertainty, may finally reveal their true identity through the groundbreaking capabilities of the James Webb Telescope. This chapter explores what this new image signifies, how it addresses a decades-old enigma, and why it matters for our understanding of the universe. For years, astronomers have puzzled over the little red dots that appear in deep space images. These dots, often seen in photographs from the Hubble Space Telescope, are faint, reddish specks that seem to defy easy classification. Early observations suggested they could be distant stars, planetary nebulae, or even rogue planets, objects that have been ejected from their home systems and drift through space in solitude. However, their exact nature remained elusive, partly because the technology of the time couldn't resolve them with enough clarity. The James Webb Space Telescope, with its advanced infrared capabilities and unprecedented resolution, has now provided a new perspective on these mysterious points of light. The key to unraveling the mystery lies in the nature of light itself. When we look at distant objects in the universe, their light has been traveling for billions of years to reach our eyes. As these objects move away from us, their light is stretched into longer wavelengths, a phenomenon known as redshift. This means that the light from the most distant objects appears redder than the light from nearby ones. The little red dots in space photographs are likely the result of this redshift, with their reddish hue indicating they are incredibly far away. But while the color suggests distance, it doesn't immediately tell us what these objects are. That's where the James Webb Telescope's unique capabilities come into play. The James Webb Space Telescope is designed to peer into the universe's earliest epochs, a task that requires it to detect light in the infrared spectrum. Unlike visible light, which can be blocked by dust and gas in space, infrared light can pass through these obstacles, revealing structures and objects that are otherwise hidden. This makes the telescope particularly adept at studying the early universe, where the first galaxies were forming. The new image, captured by Webb's powerful instruments, has allowed scientists to analyze these red dots with greater precision than ever before. By examining their light signatures, researchers have begun to piece together what these objects might be. One of the most compelling possibilities is that these little red dots are not individual stars or planets, but rather entire galaxies. The James Webb Telescope's ability to resolve fine details means that what appeared as a single point of light in previous images could, in reality, be a cluster of stars and gas clouds. This aligns with the idea that these objects are among the most distant known galaxies, their light having traveled for billions of years to reach us. Such galaxies are crucial for understanding the early universe, as they represent the building blocks of the cosmic web that formed in the first few 100 million years after the Big Bang. By studying these distant galaxies, scientists can gain insights into how the first stars and galaxies formed and how they evolved over time. Another angle of investigation involves the possibility that these red dots are not galaxies at all, but rather something else entirely. Some scientists have speculated that they could be rogue planets that have been thrown out of their home systems and now wander the galaxy in isolation. These objects, if they exist, would be incredibly cold and dark, but their presence could be detected through their gravitational effects on nearby stars or by their faint glow in the infrared spectrum. However, the James Webb Telescope's data suggests that this explanation may not fully account for the observed characteristics of the red dots. The light signatures and spatial distribution of these points of light point more strongly toward the presence of galaxies rather than isolated planetary bodies. The implications of this discovery extend beyond the immediate identification of these objects. By confirming that these red dots are distant galaxies, the James Webb Telescope is providing a new window into the early universe. These galaxies, which are so far away that their light has taken billions of years to reach us, offer a unique opportunity to study the conditions of the cosmos in its infancy. For example, the light from these galaxies can reveal details about the rate of star formation, the distribution of dark matter, and the processes that led to the formation of the first galaxies. Such insights are critical for refining our models of cosmic evolution and understanding how the universe has changed over time. Moreover, the ability to resolve these distant objects with such clarity highlights the transformative power of the James Webb Telescope. Previous telescopes, including the Hubble Space Telescope, have provided invaluable data, but they have limitations in terms of resolution and sensitivity. The James Webb Telescope, with its larger mirror and advanced instruments, can detect fainter objects and capture more detailed images, allowing scientists to study the universe in ways that were previously impossible. This new image is a testament to the capabilities of this technology and its potential to revolutionize our understanding of the cosmos. The journey to uncover the true identity of the little red dots is a reminder of how much remains to be discovered about the universe. While the James Webb Telescope has provided a significant breakthrough, there is still much work to be done. Scientists will need to analyze the data from this image in greater detail, comparing it with other observations and simulations to build a more complete picture. This process of inquiry and discovery is at the heart of scientific exploration, and it underscores the importance of continued investment in space telescopes and observational technology. In conclusion, the new image from the James Webb Space Telescope marks a pivotal moment in the study of the universe. By revealing the true identity of the little red dots, it has opened new avenues for research and deepened our understanding of the cosmos. These distant galaxies, once shrouded in mystery, now offer a glimpse into the early universe and the processes that shaped it. As scientists continue to analyze the data and explore the implications of this discovery, they are not just answering questions about the past, they are laying the groundwork for future discoveries that will continue to expand our knowledge of the universe. The journey of exploration is far from over, and with tools like the James Webb Telescope, the possibilities are as boundless as the stars themselves. For decades, astronomers have been captivated by these faint, red specks in space objects so distant and dim that they've long remained enigmatic. Known as the little red dots, they first emerged in early Hubble Space Telescope images, appearing as tiny, glowing smudges scattered across the cosmos. But their true nature has eluded scientists, hidden behind layers of cosmic dust and the limits of previous technology. Now, the James Webb Space Telescope, the most advanced observatory ever launched, has begun to peel back that veil. What started as a mystery has become a revelation, and the journey to uncover the truth is a story of ingenuity, patience, and the relentless pursuit of knowledge. At the heart of this breakthrough lies the James Webb Space Telescope itself, a marvel of engineering and science. Launched in 2021, Webb is designed to peer deeper into the universe than any telescope before it. Its primary mirror, over 21 feet wide, collects light from the faintest and farthest objects, while its suite of advanced instruments captures data across infrared wavelengths. Unlike the Hubble telescope, which operates primarily in visible and ultraviolet light, Webb's infrared capabilities allow it to see through the cosmic fog that obscures the early universe. This is crucial because the little red dots are thought to be among the oldest stars or stellar remnants, their light stretched into the red end of the spectrum by the expansion of the universe. To study them, scientists needed a telescope capable of detecting such faint, distant signals, and Webb was built for that exact purpose. The process of identifying these objects began with careful observation. When Webb's first images were released in 2022, they revealed a tapestry of galaxies, nebulae, and distant stars. But the little red dots were not immediately obvious. They required targeted observations, precise calibration, and a deep understanding of how light behaves in space. Scientists knew that these objects were likely to be extremely faint, requiring Webb's instruments to operate at their peak sensitivity. The near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, two of Webb's primary tools, were critical. NIRCam captures light in the near-infrared range, allowing it to detect heat signatures from distant stars, while MIRI's longer wavelengths can penetrate dense interstellar dust, revealing structures hidden from view. Together, these instruments provided the clarity needed to study the little red dots in unprecedented detail. But even with such powerful tools, the challenge was immense. The little red dots are so faint that they blend into the background of the universe, making them difficult to distinguish from other celestial objects. To isolate them, scientists employed a technique known as coronagraphy. This method uses a special mask, or coronagraph, to block the light from bright stars, allowing fainter objects nearby to emerge. Webb's coronagraphs are among the most advanced ever built, capable of suppressing starlight by a factor of billions. This enabled researchers to observe the little red dots without the overwhelming glare of their host stars, revealing details that had previously been invisible. Once the images were captured, the next step was analysis. The data from Webb's instruments is vast. Each observation generates terabytes of information. Scientists used sophisticated software to process these data, filtering out noise and identifying patterns. Machine learning algorithms played a key role, helping to classify objects based on their light signatures. By comparing the data to known stellar models, researchers could determine whether these objects were young stars, brown dwarfs, or something entirely new. The process was meticulous, requiring cross-referencing with existing databases and simulations to ensure accuracy. Every pixel in the image held a story, and unraveling that story required both computational power and human insight. One of the most significant breakthroughs came when scientists realized the little red dots might be young stars forming in distant galaxies. These stars, still shrouded in protoplanetary disks, emit light at specific wavelengths that can be detected by Webb's instruments. However, confirming this hypothesis required more than just observation. It demanded a deeper understanding of the physical processes at play. By analyzing the light spectra of these objects, researchers could determine their temperature, composition, and age. This spectral analysis revealed that the little red dots were indeed young stars, their light stretched into the infrared due to the universe's expansion. The discovery was a testament to the power of Webb's technology, as well as the dedication of the scientists who spent years refining their methods. The timeline of this discovery is as much about patience as it is about innovation. Webb's launch in 2021 marked the beginning of a new era in astronomy, but the telescope needed time to settle into its orbit and stabilize. The first images, released in 2022, were a milestone, but they were just the beginning. The little red dots required sustained observation, with multiple imaging sessions spread over months to capture the full complexity of these objects. Each new dataset added layers to the puzzle, allowing scientists to refine their models and test their hypotheses. The process was iterative. Initial findings were met with questions, leading to further observations, and so on. This cycle of discovery and refinement is a hallmark of scientific progress, and it was no different here. Collaboration was another key factor. The identification of the little red dots was not the work of a single team but a collective effort spanning multiple institutions and disciplines. Astronomers, data scientists, and engineers worked in tandem, sharing insights and resources to tackle the challenges of analyzing Webb's data. International partnerships also played a role, with researchers from around the world contributing to the effort. This global collaboration underscored the importance of teamwork in modern science, where the scale of the questions often outstrips the capabilities of any single lab or institution. As the analysis progressed, the implications of the discovery became clear. The little red dots are not just distant stars, they are windows into the early universe, offering clues about how stars form and evolve. By studying these objects, scientists can better understand the conditions that gave rise to the first galaxies and the processes that shaped the cosmos. Moreover, the techniques developed to identify them have broader applications, from mapping dark matter to searching for exoplanets. The methods used to isolate and analyze the little red dots are now being applied to other mysteries in the universe, demonstrating the far-reaching impact of this work. Yet, the journey is far from over. While the little red dots have been identified as young stars, many questions remain. Are there other types of objects that have been overlooked? Could some of these dots be entirely different phenomena, such as rogue planets or distant quasars? The answers will require even more advanced technology and deeper analysis. Webb's mission is ongoing, and future observations will undoubtedly uncover new surprises. The telescope's ability to peer into the universe's past is a reminder that the cosmos is still full of mysteries waiting to be solved. In the end, the story of the little red dots is a story of human curiosity and technological triumph. It is a testament to the power of science to transform the unknown into the understood. The James Webb Space Telescope has not only revealed these objects but has also opened new frontiers in our exploration of the universe. As scientists continue to analyze the data, they are not just uncovering the secrets of the past, they are laying the groundwork for future discoveries. The cosmos, vast and unyielding, still holds countless mysteries, and with tools like Webb, the journey of discovery is only just beginning. The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, has long been a tool for peering into the cosmos' most obscured corners. But recently, its latest image has stirred the scientific community by offering a tantalizing glimpse into the enigmatic little red dots that have captivated astronomers for decades. These tiny, glowing specks, once thought to be mere fragments of distant stars or perhaps rogue brown dwarfs, may now be revealing their true identity, shedding light on fundamental questions about the birth of stars, the structure of galaxies, and the very fabric of the universe. To understand why this discovery matters, we must first delve into the science that makes these dots so significant. At the heart of this mystery lies the nature of star formation, a process that has shaped the universe since its earliest moments. Stars are born in vast, dusty nurseries known as molecular clouds, where gravity pulls gas and dust together to form dense cores. These cores, if they accumulate enough mass, collapse under their own gravity, igniting nuclear fusion and giving rise to a star. But the journey from a molecular cloud to a fully formed star is complex, and the little red dots may hold clues to this intricate process. Infrared light, which the James Webb Telescope is optimized to detect, is key to unraveling this mystery. Unlike visible light, which is easily scattered by interstellar dust, infrared wavelengths can penetrate these dusty veils, revealing structures hidden from our view. This capability allows the telescope to peer into regions where star formation is actively occurring, offering a window into the early stages of stellar birth. The little red dots could be protostars, nascent stars still in the process of gathering mass, or perhaps even planetary disks, the cradles of future planetary systems. Their red color, a signature of cooler temperatures, suggests they may be in the early phases of their life cycle, still surrounded by the remnants of their natal clouds. But what makes these dots particularly intriguing is their potential to challenge existing theories about star formation. For decades, astronomers have studied star-forming regions like the Orion Nebula, where young stars and protostars are visible in visible light. However, these regions are often shrouded in dense dust, making it difficult to observe the full extent of activity. The James Webb Telescope's ability to capture high-resolution infrared images has now allowed scientists to see beyond the surface, revealing structures that were previously hidden. This has led to the possibility that the little red dots are not isolated stars but part of a larger, interconnected network of activity. For instance, they could be part of a star-forming cluster, where multiple protostars are interacting through gravitational forces, influencing each other's development. Alternatively, they might be the remnants of massive star-forming events, where the collapse of a single cloud gave rise to multiple stars in a tight-knit system. Such discoveries would have profound implications for our understanding of how stars form in different environments. In particular, they could help clarify the role of massive stars in shaping their surroundings. Massive stars, which are rare but influential, emit intense radiation and stellar winds that can ionize nearby gas, creating regions of ionized hydrogen known as H2 regions. These regions are critical for understanding the life cycles of stars and their impact on galaxy evolution. If the little red dots are part of such a system, their presence could indicate the presence of a massive star or a cluster of massive stars, offering insights into the dynamics of these powerful objects. Moreover, the study of these dots could also shed light on the distribution of dark matter in the universe. Dark matter, though invisible, exerts gravitational effects that shape the structure of galaxies. By observing the motion of gas and stars in star-forming regions, astronomers can infer the presence of dark matter. If the little red dots are part of a region with an unusually high concentration of dark matter, this could provide new clues about the nature of this elusive substance. The significance of these findings extends beyond the immediate study of star formation. Understanding the processes that govern the birth of stars is crucial for comprehending the life cycles of galaxies. Stars are the engines of galactic evolution, providing energy through their radiation and contributing to the chemical enrichment of the universe through supernovae. By studying how stars form in different environments, astronomers can better model the evolution of galaxies over cosmic time. The James Webb Telescope's ability to observe distant, ancient star-forming regions is particularly valuable in this regard. These regions, located in the early universe, offer a glimpse into how star formation processes have changed over billions of years. If the little red dots are part of such a distant system, their properties could reveal how the conditions for star formation have evolved, providing insights into the history of the universe. Furthermore, the study of these dots could also have implications for the search for exoplanets. Many exoplanets are found in the habitable zones of their host stars, where conditions are just right for liquid water to exist. Understanding the environments in which stars form is essential for identifying potential planetary systems. If the little red dots are part of a star-forming region with a high density of protostars, this could indicate a rich environment for planetary formation, increasing the chances of finding exoplanets in such systems. The James Webb Telescope's ability to detect the faint light of young planets around these stars could further enhance our understanding of planetary systems. However, the significance of these findings is not limited to the technical capabilities of the telescope. They also highlight the importance of continued exploration and the iterative nature of scientific discovery. For centuries, astronomers have built upon the work of their predecessors, refining theories and expanding our knowledge of the universe. The little red dots represent a new chapter in this story, challenging existing assumptions and opening up new avenues of research. As scientists analyze the data from the James Webb Telescope, they may uncover patterns or anomalies that were previously overlooked, leading to breakthroughs in our understanding of the cosmos. This process underscores the collaborative and dynamic nature of scientific inquiry, where each new discovery builds on the foundation laid by previous generations of researchers. In conclusion, the James Webb Telescope's latest image of the little red dots is more than just a stunning visual. It is a gateway to deeper questions about the origins of stars, the structure of galaxies, and the fundamental forces that shape the universe. By leveraging the power of infrared astronomy, the telescope has provided a unique perspective on star-forming regions, revealing details that were once hidden from our view. The potential revelations about these dots could reshape our understanding of stellar evolution, the role of dark matter, and the conditions necessary for planetary systems to form. As we continue to explore the cosmos with tools like the James Webb Telescope, we are reminded that the universe is a vast, complex tapestry, and each new discovery brings us closer to unraveling its mysteries. For decades, the night sky has been a canvas of mystery, where the faintest glimmers of light have sparked human curiosity. Among the most enigmatic features in astronomical images are those elusive little red dots, tiny, glowing specks that have puzzled scientists for years. These dots, often seen in deep space photographs, have long been a subject of speculation. Are they distant stars, ancient remnants of cosmic explosions, or something entirely new? The recent image captured by the James Webb Space Telescope has reignited this question, offering a glimpse into the past that could finally unravel their true identity. But to understand why this moment is so significant, we must first look back at the journey of human exploration of the cosmos and how our understanding of these tiny red dots has evolved over time. The story begins with the earliest days of space telescopes, when humanity first looked beyond the limits of the naked eye. In the 1970s and 1980s, the development of infrared astronomy opened a new window into the universe. Telescopes like the Infrared Astronomical Satellite, IRIS, launched in 1983, were among the first to systematically map the infrared sky. These missions revealed that the universe is filled with objects that emit light in wavelengths invisible to the human eye, objects like cool stars, dusty nebulae, and young stellar systems. Yet, even with these early breakthroughs, the little red dots remained a puzzle. Their faint glow and distant location made them difficult to study, and their exact nature was unclear. The Hubble Space Telescope, launched in 1990, marked a turning point in our ability to observe the cosmos. With its powerful optical instruments, Hubble provided stunning images of distant galaxies, nebulae, and star-forming regions. However, its primary focus was on visible and ultraviolet light, which limited its ability to detect certain phenomena. For example, young stars often shroud themselves in thick clouds of dust, blocking visible light but allowing infrared radiation to escape. This meant that while Hubble could capture the glow of mature stars, it struggled to see the earliest stages of star formation, the very processes that might explain the little red dots. Enter the Spitzer Space Telescope, launched in 2003. Spitzer was designed specifically to observe the universe in infrared light, and it became a crucial tool for studying the birth of stars and planets. Its observations revealed that many of these little red dots were likely young stars still forming within dense clouds of interstellar gas and dust. These protostars, as they are called, emit heat in the infrared spectrum, making them visible to instruments like Spitzer. However, Spitzer's relatively small mirror and limited resolution meant that these objects often appeared as faint, diffuse sources rather than distinct points of light. This ambiguity left room for speculation. Were these dots truly young stars, or could they be something else entirely? The search for answers led to the development of more advanced telescopes, but the quest for clarity was far from over. In the 2010s, the James Webb Space Telescope was conceptualized as a successor to Hubble and Spitzer, with a primary goal of studying the early universe. However, its capabilities extended beyond that. With a mirror 6 times larger than Hubble's, JWST was designed to capture light from the faintest and most distant objects. Its infrared instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, were built to detect the faintest signals from the cosmos. This made JWST uniquely suited to study the little red dots, objects that had previously eluded detailed observation. The key to understanding these dots lies in the nature of infrared light itself. Unlike visible light, which is easily scattered by interstellar dust, infrared radiation can pass through these dusty clouds, revealing the hidden processes of star formation. When a young star begins to form, it is often surrounded by a cocoon of gas and dust. This material absorbs the star's visible light but radiates heat in the infrared. As the star grows, it begins to heat up the surrounding material, creating a glowing halo that can be detected by infrared telescopes. These halos, combined with the star's own infrared glow, create the faint, red-tinged points of light that have captivated astronomers for years. But even with JWST's advanced capabilities, the little red dots have remained a subject of debate. Some scientists have suggested that these dots could be not just stars, but entire systems of stars forming together. Others have proposed that they might be brown dwarfs, failed stars that are too small to sustain nuclear fusion. These objects, which are often referred to as failed stars, emit very little light and are difficult to detect. However, their infrared signatures could resemble the little red dots observed in space. This ambiguity highlights the complexity of the issue and the need for more precise data. The recent image from JWST has brought new hope to this quest. By capturing unprecedented detail in the infrared spectrum, the telescope has allowed scientists to study these dots with greater clarity than ever before. The image, which has been widely shared as the space photo of the week, reveals intricate structures that suggest the presence of young stars and their surrounding environments. The ability to resolve these details has opened the door to new hypotheses about the nature of these objects. For example, the presence of certain spectral features in the image could indicate the presence of molecules or dust that are characteristic of star-forming regions. This moment is not just about solving a mystery, it is also a testament to the evolution of our tools for exploring the universe. From the early infrared satellites to the powerful observatories of today, each step forward has brought us closer to understanding the cosmos. The little red dots have been a part of this journey, serving as a reminder of how much we still have to learn. As we look to the future, the data from JWST will undoubtedly shape our understanding of star formation and the early universe. For now, the image stands as a symbol of human curiosity and the endless pursuit of knowledge that drives us to explore the stars. The James Webb Space Telescope has captured an image that has sparked a wave of curiosity and debate among astronomers. At the center of this intrigue are the so-called little red dots, faint, glowing specks that have puzzled scientists for years. These objects, first spotted in earlier space images, have long been a mystery. Are they distant stars, ancient brown dwarfs, or something entirely new? The latest image from JWST, with its unparalleled resolution and sensitivity, may finally shed light on their true nature. But even as scientists analyze the data, the questions remain: what exactly are these dots, and what do they tell us about the universe? This chapter explores the open questions, the scientific debates, and the mysteries that still linger in the wake of this groundbreaking image. For decades, astronomers have studied the cosmos through telescopes that have revealed the vastness of space and the complexity of celestial phenomena. Yet, some objects have remained stubbornly elusive. The little red dots, a term popularized by early space missions, refer to faint, reddish specks that appear in images of distant star-forming regions. These dots are not stars in the traditional sense, nor are they planets. They are too dim to be classified as stars, and their reddish hue suggests they are cooler than typical stars. For years, scientists have speculated about their origins. Some thought they might be young stars still shrouded in gas and dust, while others proposed they could be brown dwarfs, failed stars that lacked the mass to sustain nuclear fusion. However, these theories remained unconfirmed, and the true nature of these dots remained a mystery. The James Webb Space Telescope, launched in 2021, has revolutionized our ability to observe the universe. Its advanced instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, allow astronomers to peer deeper into space than ever before. The latest image, released as the Space Photo of the Week, has captured these red dots in unprecedented detail. The image, which focuses on a distant region of space known as the Carina Nebula, reveals a dense cluster of stars and gas clouds. Amid this cosmic landscape, the red dots stand out, their faint glow hinting at their unique properties. But what exactly are they? Are they stars in their infancy, or something else entirely? One of the leading hypotheses is that these dots are young stars still surrounded by thick clouds of interstellar dust. In the early stages of a star's life, a protostar is often obscured by a cocoon of gas and dust, making it difficult to observe directly. The reddish color of these objects could be due to the way light is scattered by the surrounding material, creating an illusion of color. However, this theory faces challenges. The light from these objects is too faint to be explained by typical young stars, and their distribution in the image suggests they may not be randomly scattered throughout the nebula. Instead, they seem to cluster in specific regions, which could indicate a different origin. Another possibility is that these dots are brown dwarfs, objects that are too massive to be planets but not massive enough to sustain nuclear fusion like stars. Brown dwarfs are often referred to as failed stars because they lack the mass required to ignite the fusion reactions that power stars. They emit very little light, primarily in the infrared spectrum, which aligns with the reddish hue observed in these dots. However, brown dwarfs are typically much cooler than the objects in this image. The temperature of these dots suggests they are warmer than typical brown dwarfs, raising questions about their classification. Moreover, the presence of so many brown dwarfs in a single region of space would be unusual, as they are typically sparse in such environments. The scientific community is divided on the true identity of these dots. Some researchers argue that they could be a new class of celestial objects, distinct from both stars and brown dwarfs. This theory is supported by the fact that these objects emit light at wavelengths that do not match known stellar or substellar objects. The James Webb Telescope's ability to detect infrared light has allowed scientists to observe these objects in greater detail, revealing subtle characteristics that were previously hidden. However, the data is still incomplete, and more observations are needed to confirm these findings. The debate is further complicated by the fact that some of these objects may be part of a larger population that has yet to be fully understood. One of the most intriguing aspects of this discovery is its potential implications for our understanding of star formation. If these dots are indeed young stars or brown dwarfs, they could provide valuable insights into how stars and planets form in dense regions of space. However, if they are something entirely new, they could challenge existing models of stellar evolution. The Carina Nebula, where these objects were observed, is a well-known region of active star formation. It is home to massive stars, young stellar objects, and intricate networks of gas and dust. The presence of these red dots in such an environment suggests that they may be part of a complex web of interactions that shape the birth of stars and planets. Despite the excitement surrounding this discovery, there are still many unresolved questions. For example, how many of these objects are there in the Carina Nebula, and how do they compare to other regions of space? Are they unique to this particular area, or do they represent a broader phenomenon? Additionally, what role do these objects play in the overall structure of the nebula? Are they influencing the formation of other stars, or are they simply remnants of a chaotic past? These questions highlight the complexity of the issue and the need for further research. The scientific process is inherently iterative, and the discovery of these red dots is no exception. While the James Webb Telescope has provided a wealth of new data, the interpretation of this data is still in its early stages. Scientists are working to refine their models and test various hypotheses. Some are using simulations to recreate the conditions of the Carina Nebula and see how these objects might form. Others are comparing the data to observations from other telescopes to see if similar objects exist elsewhere in the universe. The goal is to build a comprehensive understanding of these objects and their place in the cosmic hierarchy. The mystery of the little red dots is a testament to the enduring nature of scientific inquiry. Even with the most advanced technology, there are still gaps in our knowledge, and some of the most profound discoveries often begin with questions that seem impossible to answer. The James Webb Telescope has opened a new window into the universe, allowing us to see things we never could before. But as with any scientific breakthrough, this discovery is just the beginning. It has raised more questions than it has answered, and it has inspired a new generation of astronomers to explore the unknown. In the end, the true significance of these red dots may not lie in their immediate classification, but in the way they challenge our understanding of the universe. They remind us that the cosmos is full of surprises, and that even the most advanced tools can only take us so far. The journey to uncover their secrets is just beginning, and it promises to be as exciting as it is challenging. As scientists continue to analyze the data and refine their theories, one thing is clear: the universe still holds many mysteries, and the quest to solve them is far from over. As we look ahead, the journey to unravel the mysteries of these little red dots is far from over. The James Webb Space Telescope has already opened a new window into the cosmos, but its revelations are just the beginning. The next chapters in this story will be written by future missions, advanced instruments, and groundbreaking observations that could either confirm, expand, or even challenge what we've learned so far. Let's take a closer look at what's coming next and how these developments might reshape our understanding of the universe. One of the most anticipated next steps is the launch of the Nancy Grace Roman Space Telescope, a mission set to begin operations in the mid-2020s. This telescope, named after the former NASA deputy administrator, is designed to conduct wide-field surveys of the sky, capturing vast swaths of data with unprecedented precision. While its primary focus is on dark energy and exoplanet detection, its capabilities could prove invaluable in studying the red dots. By measuring the brightness variations of these objects over time, the Roman telescope could help determine whether they are indeed exoplanets or something entirely different. For instance, if these dots are young stars or brown dwarfs, their light might exhibit specific patterns that could be detected through long-term monitoring. The Roman telescope's ability to observe large areas of the sky simultaneously also means it could identify additional candidates that might share similar characteristics, providing a broader context for the JWST's findings. Meanwhile, on the ground, the Extremely Large Telescope, ELT, in Chile is preparing to revolutionize our ability to study distant celestial objects. Scheduled to begin operations in the late 2020s, the ELT will be the largest optical telescope ever built, with a mirror over 39 meters in diameter. Its advanced adaptive optics system will allow it to pierce through Earth's atmospheric distortions, capturing images with a clarity that rivals space-based telescopes. If the red dots are exoplanets, the ELT could provide critical follow-up observations. For example, it might analyze the light reflected off these objects to determine their composition or detect signs of atmospheric features like clouds or gases. This would complement the JWST's infrared data, offering a more complete picture of these distant worlds. Additionally, the ELT's ability to observe multiple objects simultaneously could help astronomers identify patterns or correlations among the red dots, potentially revealing whether they belong to a larger population of similar objects. Another key player in the coming years is the Plato mission, a European Space Agency (ESA) project set to launch in the 2020s. Plato, which stands for Plato, is designed to search for exoplanets around nearby stars, with a particular focus on those that could potentially support life. Its instruments will use the transit method to detect planets as they pass in front of their host stars, but its capabilities extend beyond that. The mission's wide field of view and high sensitivity could allow it to detect subtle changes in starlight that might indicate the presence of small, rocky planets or even gas giants similar to the red dots observed by JWST. If the red dots are indeed exoplanets, Plato's data could help refine their orbital parameters, atmospheric properties, and potential habitability. Moreover, Plato's ability to study multiple stars at once might uncover additional candidates that share similar traits, further validating or expanding the initial findings from JWST. The James Webb Space Telescope itself is not done yet. While its current observations have already provided groundbreaking insights, the telescope's continued operations will play a crucial role in deepening our understanding of these red dots. Over time, JWST could conduct more detailed spectroscopic analyses of these objects, breaking down their light into its component wavelengths to reveal their chemical makeup. For example, if the red dots are exoplanets, their atmospheres might contain molecules like water vapor, methane, or carbon dioxide signatures that could indicate geological activity or even the presence of life. By comparing these spectral signatures with those of other known exoplanets, astronomers could determine whether these objects fit into existing categories or represent entirely new classes of celestial bodies. Additionally, JWST's ability to observe these objects over multiple epochs might reveal changes in their appearance, such as variations in brightness or color, which could hint at dynamic processes like stellar flares, planetary weather systems, or even the presence of moons. Beyond these missions, the coming decades may see the development of even more advanced instruments capable of addressing questions that current technology cannot yet answer. One such concept is the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, a proposed next-generation space telescope that could be launched in the 2030s or 2040s. LUVOIR's design would allow it to study exoplanet atmospheres with unprecedented resolution, potentially detecting biosignatures, molecular indicators of life on distant worlds. If the red dots are exoplanets, LUVOIR's capabilities could be instrumental in determining whether they harbor conditions suitable for life. Similarly, the Habitable Worlds Observatory, HabEx, another proposed mission, aims to directly image exoplanets and analyze their atmospheres for signs of biological activity. These missions, while still in the conceptual phase, represent the kind of technological leap that could transform our understanding of the red dots and their potential significance. However, the story of these red dots is not solely about confirming their identities. Future observations might also challenge existing assumptions and force scientists to rethink long-held theories. For instance, if the red dots are not exoplanets but something entirely different, such as young stars, brown dwarfs, or even remnants of ancient supernovae, this could shift our understanding of star formation, planetary systems, or the distribution of matter in the universe. The data from upcoming missions could reveal unexpected patterns or anomalies that require new models to explain. For example, if the red dots are brown dwarfs, their presence might indicate a previously unknown population of these objects in our galaxy, altering our estimates of their abundance. Alternatively, if they are the remnants of distant supernovae, this could provide insights into the life cycles of stars and the role of supernovae in shaping the cosmos. Another critical aspect of future research will be the integration of data from multiple missions and instruments. The red dots observed by JWST are part of a larger puzzle that may require a multifaceted approach to solve. By combining the strengths of space-based and ground-based telescopes, as well as data from other observatories, astronomers can build a more comprehensive picture of these objects. For instance, while JWST provides detailed infrared data, ground-based telescopes like the ELT or the upcoming Giant Magellan Telescope, GMT, could offer complementary observations in visible and ultraviolet wavelengths. These combined datasets might reveal features that are invisible to a single instrument, such as the presence of dust clouds, magnetic fields, or interactions between celestial bodies. The ability to cross-reference data from different sources will be essential in distinguishing between competing hypotheses and narrowing down the possible explanations for the red dots. In addition to observational missions, the coming years may also see advancements in computational modeling and data analysis techniques. As the volume of astronomical data continues to grow, new algorithms and machine learning tools will be developed to process and interpret this information more efficiently. These tools could help identify subtle patterns in the data that might otherwise go unnoticed, such as faint signals from distant exoplanets or unusual variations in starlight. For example, if the red dots are exoplanets, machine learning algorithms might be able to detect faint atmospheric features or predict the timing of their transits with greater accuracy. These advancements will not only aid in the study of the red dots but also contribute to broader efforts in astrophysics, from understanding the structure of the universe to searching for extraterrestrial life. Finally, the study of these red dots could have implications beyond astronomy, influencing fields such as planetary science, astrobiology, and even philosophy. If these objects are indeed exoplanets, their characteristics could provide clues about the diversity of planetary systems in the galaxy and the potential for life beyond Earth. For instance, if the red dots are rocky planets with atmospheres rich in certain gases, this might suggest conditions favorable for life. Conversely, if they are gas giants or barren worlds, this could highlight the vast range of environments that exist in the universe. Such findings could reshape our understanding of where life might be possible and how common such conditions might be. Moreover, the search for these objects could inspire new questions about the origins of life, the role of cosmic events in shaping planetary systems, and the long-term fate of stars and planets. As we look to the future, the story of these little red dots is far from over. The next chapters will be written by the next generation of telescopes, the ingenuity of scientists, and the relentless pursuit of knowledge. Whether these dots are exoplanets, brown dwarfs, or something entirely new, their discovery has already sparked a wave of curiosity and excitement. The coming years will bring new tools, new data, and new possibilities, each step bringing us closer to answering the question, what exactly are these little red dots, and what do they tell us about the universe we live in? New James Webb Telescope image may reveal the true identity of little red dots. Space photo of the week. This part of our deep dive into new James Webb Telescope image may reveal the true identity of little red dots. Space photo of the week focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.